Okay guys, so welcome back. In this lecture we are going to continue from MCQs number 21 to 30 and AS Physics paper 1 variant 1 May June 2010. Alright, 9701. Sorry, 9702 AS Physics. Alright, so now let's get started. In the stress string experiment on the metal wires, the stress axis is marked with the units of 10 raised to the power of 8 pascals, and the strain axis is marked as a percentage. This is shown for a particular wire in this diagram. All right, so it's given stress against strain graph. Okay, what is the value of the Young's modulus for the material of this wire? All right, guys, so Young's modulus by definition is the ratio of stress to strain. Okay, stress upon strain is Young's modulus. All right, so just consider any point over here. Okay, so this last point over here, the strain is 5%. Okay, guys, this is at 5%. 5% in numerical terms would mean 0.05. All right, 0.05. 5% means 0.05, and strain at this point is 3 raised to the power of 8. All right, so you have the value of stress, you have the value of strain. Use them in the formula of the Young's modulus to get your final answer. Okay, stress is 3 raised to the power of 8, and if you divide it by 0.05, you will end up getting 6 raised to the power of 9 pascals. Right, so option D is correct. Let's move on to the next MCQ. 22. A diagram shows a steel wire clamped at one end and tensioned at the other by a weight hung over a pulley. Alright, so this is basically vibration generator, and it's moving up and down, and over here it is fixed. The wire is fixed at this end by this weight over here, whereas on the other end there is a vibrator attached to it, and this vibrator is producing some waves inside the wire. The vibration, and this is actually a stationary wave setup. All right, this is the setup of a stationary wave, and you guys must have done this in your theory part as well. Right, now let's see. A vibration generator is attached to the wire near the clamp end. Okay, a stationary wave. Okay, he even mentioned it in the question. A stationary wave with one loop is produced. Okay, this is actually the first loop. It's called the first harmonic. The first harmonic is produced over here. All right, and the frequency of the vibration of the generator is f. All right, so if the frequency of the vibration of the generator of the first loop is f, this is actually your fundamental frequency. So if you want to form next more loops in the stationary wave, then you must adjust the frequency of this vibrator to multiples of this f. Okay, so if you want more stationary waves with greater number of loops, then you must use vibration frequency to be 2f. You must increase it to 2f or 3f or 4f or something like that, multiples of f. Okay, now which frequency should be used on the stationary wave to produce two loops? All right, now you want to produce two loops, so it's going to be 2f. Two loops, 2f. It works like this. If you want one loop, it's going to be just f, but if you want two loops, it's going to be 2f for a string. Okay, for a string basically. And this condition actually changes when you are dealing with open pipes. Okay, and we'll talk about them when the question about the open pipes come. Right, now let's move on to the next MCQ. Again, an MCQ from the waves chapter. Diagram 1 shows a ripple tank experiment in which a plane waves are diffracted through narrow slit in a metal sheet. All right, this is diagram 1. Plane waves are formed and they are diffraction has occurred. Okay, diffraction basically spreading of wave when they pass through a narrow opening into a geometrical shape or geometrical shadow. Now diagram 2 shows the same tank with a slit that has a greater width. All right, so it's actually the waves are more wider rather than more narrow. Okay, in which case diffraction over here is lesser. Okay, now the wave pattern of the wave incident on the slit and the emergent pattern are shown over here. Which action would cause the waves in diagram 1 to be diffracted less and so produce an emergent pattern closer to that in diagram 2? Okay, how can we decrease the degree of diffraction in diagram 1? Okay, guys, remember one thing. The smaller the slit size, the greater the diffraction, and the slit size must be comparable to the wavelength of the wave. Okay, so if you reduce it even more, the degree of diffraction will increase. Okay, so now let's look at the answer options one by one. Okay, now let's look at the options one by one. Okay, let's look at first option, increasing the frequency of the vibration of the bar. Okay, this the examiner is indirectly telling us that we know the formula V is equals to F lambda. The frequency and wavelengths are inversely related from this formula so long as the speed of the wave is constant. Okay, so now if they are increasing the frequency, this means that the wavelength is actually decreasing. If the wavelength is decreasing, what would happen? Decrease in wavelength would mean that this slit size has actually become greater than the wavelength of the wave that is approaching here. So this is again satisfying our condition. So therefore A is the correct option. Now let's look at Bravo. Increasing the speed of the waves. Okay, speed of the wave is gonna be will increase, but it is proportional to the product of frequency and wavelength. So both of them will actually, it will have no effect on diffraction. Okay, it won't. Then reducing the amplitude of vibration of the bar. Okay, if you decrease the amplitude of vibration, it will still not have any effect on the wavelength. This will just decrease its maximum vertical displacement. This will just become a smaller wavelength wave, but it's a smaller displacement, smaller vertical displacement wave will form, but the wavelength will not change. And reducing the length of the vibrating bar, again it will still not have any effect on the wavelength of the wave. So, and neither of these B, C or D have any effect on the wavelength of the wave. Answer option A is correct, because increase in frequency would actually decrease the wavelength of the wave, and if the wavelength of the wave decreases, it is equivalent to saying that the slit size has become greater than the wavelength of the wave, because decreasing the wavelength indirectly means that the slit size has become greater relative to the wavelength of the wave. So that's why option A is correct. Let's move on to the next part. 24. Electromagnetic waves for an unknown source in space were found to be significantly diffracted when passing through gaps of this order. Okay, now as I told you earlier that for diffraction, the wavelength of the wave and the slit size must be comparable with one another. Now they have given us the gaps or the slit size which do cause a diffraction of some electromagnetic waves in the space. Which type of wave are they most likely to be? All right, so this is basically something you need to learn. Okay, so in the range 10 raised to the power of minus 5. Okay, so you need to know the ranges of their wavelengths, all right, so of the wavelength of each of these waves. So now we need to we need to identify the wave which has a wavelength that is most comparable to the wavelength that's given in the question. All right, if we look at the wavelength of microwaves, the range of wavelength of microwaves is 10 raised to the power of minus 3 meters to 10 raised to the power of minus 1 meters. This is not the range that contains 10 raised to the power minus 5, so microwaves cannot be the answer. What about infrared? Actually, infrared is has a range of 10 raised to the power minus 4 to 10 raised to the power minus 6 meters. So yes, this is a possible answer, and yeah, actually C is the correct answer. Right, so because 10 raised to the power minus 4 and 10 raised to the power minus 6, this is the range that includes 10 raised to the power minus 5, and it is the most comparable range for this wavelength range. All right, so most comparable range for this wavelength that they have already given us. All right, moving on to the next MCQ. Using a monochromatic light source, interference fringes are produced on a screen placed at a distance of d from a pair of slit separation of fringes is x. A and D are now doubled. What is the new fringe separation? This is actually a condition of the Young's double slit experiment, and the formula that we use in that case is x is equals to lambda d upon A. All right, now what are they saying? What happens to a new fringe separation? Basically, they are asking what happens to x. Right, both A and D are doubled. If D is doubled and A is also doubled, they'll cancel each other out and there will be no effect. It will stay the same, it will stay X. Moving on to the next MCQ, 26. It says that two oppositely charged plates are arranged as shown over here. Alright, they are arranged. And then it says that an electron is released from rest on the surface of the negatively charged plate towards its positively charged plates. And then the question asks us that how will this force on the electron vary from its with its distance from the negatively charged plates. All right, So now as the electron moves towards this positively charged plate, this distance from the negatively charged plate will actually increase, okay? So this x has to increase. Now x is not the distance between these plates, it is the distance of the electron from this negatively charged plate. This is one thing to keep in mind. And secondly, the question asks us that what is the value of the force, how will it change with this distance of the electron from the negatively charged plate. All right guys, one thing to remember over here, that parallel plate in between parallel plates we always have a uniform electric field, right? And uniform electric field would mean that at any point in this field, the force, the magnitude of the force on the charged particle will be constant. All right, so it's going to be the force will stay constant, and option D is the correct answer. Moving on to the next MCQ 27. A diagram, in this diagram, the shaded area represents the uniform electric field directed away from the observer at right angles into the plane of the papers. All right, so basically electric field goes into the plane of the paper. All right, this is the electric field. A horizontal beam of electrons enters the field, traveling from left to right. In which direction is the beam deflected by the field? All right, now field is going into the page, right? It is going into the page and it's negatively charged. Now if the field is also wait, the field is going into the page, right? And it's actually going from uh, positive particles towards the negative particles. So if we consider this to be your page, let's assume that this is this region over here, and the positive plate is above this page and the negative plate is below the page. Only then is the case when this field will go away from within the page, right? And this is how it will point. Now if an electric field or an electric beam comes over here, electron beam, what will happen? If an electron beam comes over here, it's negatively charged, it will get attracted towards the positively charged plate, and it will go out of the plane of the paper towards this positively charged plate. All right, so it will move upwards, and after moving upwards in the plane of the paper, well, not within the plane of the paper, not downwards. All right, what about the observer? If for example we are looking from above, all right, so isn't the electron beam going towards the observer? It's going towards the observer, right? So option D should be the correct answer. Right, now let's move on to the next MCQ. 28. Diagram shows 2 points P and Q lying at 90 degrees apart on a circle of radius r. A positive point charge at the center of the circle creates an electric field of magnitude E at both P and Q. Alright, this charge over here is creating an electric field at point P and Q. Alright, now which expression gives the work done in moving the unit positive charge from P to Q? Alright, now the unit positive charge is moved from P to Q. All right, guys, one thing to note over here is that this positive charge was moved from P to Q, but did it move towards or away from this positive charge at the center? It did not. It did not move towards or it did not move away from this positively charged particle at its center. So if work is not done on this charge, or if work is not done against the charge, so if work is not done by the charge or work is not done on the charge, then there will be no change, no work will be done on this charge, because the charged particle is not moving towards charge nor is it moving away from the charge. So answer option A should be correct, because no work has been done yet. Right, now moving on to the next option, 29 and 30. Right, these are the last two MCQs for this lecture. Okay. Which row describes the circumstances under which forces act on a charged particle in a uniform electric field? Okay, charged particles. Electric field, all right. In electric fields, stationary charged particles and moving charged particles, both of them experience electric force, all right. And what about the direction of the force? All right, so it's parallel to the field or perpendicular to the field. Well, if you take an example of the field, if these are the two plates of the field, the positive plate and the negative plate, and the field is directed downwards, and if an electric beam enters the field from over here, it will move either parallel or anti-parallel to the field, but it will be parallel, right? It won't be perpendicular. Option C should be correct. Okay, both stationary and moving charges and parallel to the field. All right, now let's move on to the next. The resistance of a thermistor depends on its temperature, and the resistance of LDR depends upon the illumination. Which under which conditions will the resistance of both thermistor and LDR be the highest? All right, guys, one thing to know over here: as the temperature increases, the resistance of thermistor decreases, and as the light intensity increases, the resistance of LDR decreases. So we need the opposite effect. We need both these resistances to increase. So if we decrease the temperature, if we make it cold, only in that case will the resistance of the thermistor increase, and if we make it dark, only in that case will the resistance of LDR increase. All right. So cold and dark thermistor, temperature should be low as possible and illumination should also be low as possible. Answer option D is correct. All right, so that's it for this lecture. We'll continue from 31 to 40 in the next lecture. The link, I'll make sure to give the link in the description. Okay, guys, thank you so much.